Hi there, and welcome to Math 355. Today we are going to be covering 3.1 and 3.2 in your textbook. These two sections introduce the idea of derivative, which is something we've been talking about the entire semester, but now we're actually going to formalize it using the idea of the limit. And so to begin with, a question we want to ask is, how do we define the slope of a function? Because this is kind of a big idea. When we think about slope, we know how to do slope for lines, and we even have the old algebra 1 definition. M is equal to y2 minus y1 over x2 minus x1. We could expand that in algebra 2 using the idea of functions, but it was still really the same. How would we then vary it up to create the slope of a function like f of x equals x squared? And that's where things become a little bit more challenging, because there isn't going to be a single slope for the entire function. Instead, what we'll get is we'll get a new function which tells the slope at every single point on the curve. And that's what the derivative is. Let's see, these slopes are measured using a number of different techniques. Yeah, there's a number of different techniques that we can use to measure them. The main one, though, is going to be our derivative. And so the derivative of a function is an equation which gives the rate of change of a function. It can be used to measure rates of change in the form of physical slope, but also to calculate rates of change with respect to time. When we think about what we're going to be doing in this course, most of the time we're going to be focused on rates of change with respect to time, because we're not really interested in how one spatial component is changing with respect to another spatial component. Instead, we're interested in how blood flow is changing with respect to time. We're interested in how different proteins are changing or growing or that type of thing. And we're thinking about that, it's usually going to be population per time. The examples we'll be seeing will be using both spatial and time components, but don't let that bog you down. Really, we're just talking about an independent variable of x or t or something else as we get to weirder examples. But yeah, they're essential for understanding what we're going to be doing the rest of the semester. In many ways, derivatives are what a standard Calculus 1 course focuses on. And this is kind of like a combo Calculus 1, Calculus 2 class. And so we're going to be seeing a lot of stuff with derivatives. That said, we're going to start by going through two different formulas, which we can use to model it. This first one is great for the average rate of change, while the second one is good for the instantaneous rate of change. But both of these formulas can be used to calculate either the average rate of change or the instantaneous rate of change. And so we'll start with the average rate of change formula, the first formula. And so the average rate of change of a continuous function f of x on the interval a, b is given by the expression average rate of change equals f of b minus f of a over b minus a. Hopefully there's nothing new about this. This is just the slope equation from algebra 2. This is just the difference quotients equation from chapter 1. This is just the slope of the secant line. All of these things are the exact same thing. The one downside for this one, though, is that it requires two inputs. And that's something which makes it so that it's great for calculating average rate of change, but not so much for instantaneous rate of change. And so here's a couple of examples. Find the average rate of change of f of x equals square root of x on the interval 4, 16. And then find the slope of the secant line of f of x equals square root of x on the interval 4, 16. Note that both of those are exactly the same. And so let's see if we can figure that out. Our function f of x is square root of x on the interval 4, 16. And so in order to calculate the average rate of change of this, all we need to do is figure out our different components. And so we could say that our a value, which is our starting value, is 4. Our b value is 16. F of a is going to be equal to the square root of a, which is going to be the square root of 4, which is 2. F of b is going to be equal to the square root of 16, which is 4. So the average rate of change is equal to f of b minus f of a over b minus a. Crunching the numbers, 4 minus 2 is 2. 16 minus 4 is 12. And so we end up getting 1/6. So now the question becomes, what does this 1/6 actually represent? Because we can call it the average rate of change, but having a visual for it might be nice. And so let's go to our good friend Desmos. We'll insert our function. F of x is equal to the square root of x. And it's going from 4 to 16. And so let's put those points down, 4, 2. And then we're going to go 16, 4. There we go. And so now we can see those 2 points. The average rate of change, being 1/6, is telling us that the slope of the line going through these 2 points is 1/6. And so if we were to create the equation going through those 2 points, we would say it is y minus, how about 2 equals m times x minus 4. This would be point slope form using the 4-2 point. And then we just got that the slope connecting them is 1/6. Oh, I need to have numlock on. There we go, 1/6. And notice that using that slope, it goes through both of those points. That's what the average rate of change is. The average rate of change is saying, if this were linear, what is the slope of the line going through those 2 points? That is also the slope of the secant line, because remember, these 2 things are the same thing. 3 looks a little bit more interesting. Consider that you wish to find the average rate of change of f of x equals square root of x on the interval from 4 to b, where b is some value between 0 and infinity. Create an expression for the average rate of change. So let's see if we can figure that one out. And so for 3, it's still going to be f of x is equal to square root of x. But now it's on the interval from 4 to b. And so when we calculate this one out, well, again, our a is just going to be 4. Our b is now just b. Our f of a is still going to be 2. And our f of b is the square root of b. That tells us that our average rate of change is going to be equal to f of b minus f of a, which is square root of b minus 2 over b minus 4. And so this is an expression which will tell you the average rate of change on any interval. And so from 4 all of the way out to any number, this will tell us our average rate of change. And again, it might be nice to see what the visual is for this. So let's go back to our good friend Desmos. Here we go. And so let's create a new point on this graph. We're going to keep this equation here, but we're going to create a new point using the value b. And so it'll be b comma f of b. And we'll create a slider for b. What this does is this makes it so that we can move this point around wherever we want. We'll even make it blue so it matches. Now, we started with it being 16, and we said that we could figure out what the slope was for the value 16. The slope ended up being 1/6. Well, now what we have is we have a formula which will tell us what our slope is no matter what value b is. And so our slope is our average rate of change. So the average rate of change is the ratio square root of b minus 2 over b minus 4. Now this formula for the slope is going to make it so that no matter where this point is, it's always going to give us a line going through these 2 points. So if it's close, it goes through it. If it's far, it goes through it. And it does not matter where it is. It is always going to give us an equation for that slope. And so when b is equal to 165, we get that the slope, the average rate of change, is 0.06736 and so on. And so that's kind of a powerful thing. But we can go a step further. And that step further is going to come from the instantaneous rate of change. And so consider the average rate of change formula you derived in exercise 3. If we allow b to get arbitrarily close to 4, the limit will give us some value which is known as the instantaneous rate of change. Find the instantaneous rate of change when x is equal to 4. And so let's take a look at the visual for this real quick. And so the visual for this is, what if we let this b value get arbitrarily close to 4? Then what will our slope be? And if we just choose it to be exactly 4, notice that it goes undefined because we can't have that 4 in the denominator. But if we come just a hair off, we get 2.487. And if we go a little in the other direction, we get 2.509. And so it looks like it's really close to 0.25. And that would be, again, just the line connecting these two. But we get it as close as we want. We just can't be on top of it. Well, hopefully this idea of getting as close as you want is something familiar, because that's what we did in chapter 2. In chapter 2, we learned about the limit. And what we're really doing is we're taking the limit of this thing. And so we are doing the limit as our b value goes to 4. And so for number 4, we are taking the limit as b goes to 4 of the square root of b minus 2 over b minus 4. And this is one which we did very similar examples to last time. The trick to simplifying this one is to use the conjugate. And so we could multiply by root b plus 2 and root b plus 2. On the top, that's going to give us b minus 4. Still write our limit out there. Limit as b goes to 4 over b minus 4 square root of b plus 2. Our b minus 4s will cancel out, leaving 1 over square root of b plus 2. And now we can actually plug the 4 in. That gives us 1 over square root of 4 plus 2. Square root of 4 is 2. 2 plus 2 is 4. And so we get 1/4. Our instantaneous rate of change is 1/4. And that's what we had on our graph. And so our graph was showing that we were going to get something really close to 1/4. This is telling us that yes, the answer is 1/4. One thing to note about this, and this is where this example can become kind of difficult, is the formula we just used is great, but it only works at this one point, at the point 4,2. And so we were able to find the instantaneous rate of change at 4,2 using this formula. The limit as x goes to a of f of x minus f of a over x minus a. Ideally, we would want to figure out a formula which would tell us the instantaneous rate of change at every single point and give us a formula for the slope at every single point. This formula just doesn't quite do it. And so that's why while this formula is great for finding the average rate of change, it's not great for finding the instantaneous rate of change. Instead, we have another formula for it. And that is this one. Notice it says average rate of change second formula. And so the average rate of change second formula is the same as our difference quotient from chapter 1. It's f of a plus h minus f of a over h. And this will tell you the average rate of change from a point to some value h units away. This one, I even wrote in the notes, is a bit clunky for finding the average rate of change, because average rate of change, you really want to know what your starting and ending values are. And with this one, it gives you the starting value and it tells you how far away the second value is. That's not as useful. But this one is exceptional at finding the instantaneous rate of change. And so the instantaneous rate of change of a function, f of x, is given by this limit. The limit as h goes to 0 of f of a plus h minus f of a over h. And let's try this with the function we just worked through. So it says, find the instantaneous rate of change of f of x equals the square root of x at the point 4, 2. And so we will let f of x be equal to the square root of x. We're at the point 4, 2. And in case you need the reminder, I'll write down the difference quotient formula here. It's the limit as h goes to 0 of f of a plus h minus f of a over h. Just as a reminder of where this formula is really coming from, the formula that we were using for slope is rise over run. And that's what this corresponds to. This is saying the run is h units. And so if we know that the run is h units, the rise would be given by f of a plus h minus f of a. This would be the value at your ending part of the interval minus the y value at the start of the interval. And so change of y's over change in x's. Making it the limit as h goes to 0, though, brings that slope down to an instantaneous point. And so let's see if we can figure out how to plug in this formula into this equation. And so we know a is 4. We know f of a is equal to 2, because that's actually given to us right here. That's the point. And we could also plug in 4 into this, get square root of 4 is 2. F of a plus h is going to be the messy one, because f of a plus h, well, we know that a is 4, and so that means we're going to be plugging in 4 plus h, which gives us the square root of 4 plus h. Now we have to somehow simplify this. And so our formula, our instantaneous rate of change, I cannot wait to stop writing instantaneous rate of change and write derivative, is equal to the limit as h goes to 0 of f of a plus h, which we know to be the square root of 4 plus h, minus f of a, which is 4, over h, which is just h. That's not right. F of a wasn't 4, f of a is 2. Hopefully you're all paying attention, because I do make mistakes like that occasionally. And as we get to more and more complicated things, you might see them pop up more and more. So from here, we can then do the same trick that we did with the last one. We're going to use the conjugate. Because right now we can't plug 0 in for h. When we do that, we would be dividing by 0. It would actually be 0 over 0. And so doing the conjugate, which in this case is square root of 4 plus h plus 2, square root of 4 plus h plus 2, we end up getting in the numerator 4 plus h minus 4. And we still have our limit out in front. On the bottom, we'll just leave it gross with this h out in front. Square root of 4 plus h plus 2. And the reason we did that instead of distributing the h is because when we cancel the 4s, we'll be able to cancel those h's as well. And so we'll be able to get limit as h goes to 0 of 1 over square root of 4 plus h plus 2. And now with this, we can then plug the 0 in for h, and that will give us 1 over square root of 4 plus 2. Square root of 4 is 2, 2 plus 2 is 4. That gives us 1/4. And so again, the question becomes, what does this 1/4 represent? Well, we can go to the graph. And when we go to our graph, what we've basically created is the slope. And so the slope at that value is 1/4. And now we don't even have to worry about this b value because we're not interested in a secondary point. We just found the instantaneous rate at this point. And now what many folks think at this point is, why do we need this formula? The other formula was able to get us that 1/4 exactly the same way. And here's the key difference between that formula and this formula. This formula allows us to make it so that our starting value is general. And so here we made sure to choose 4 as our starting point. What if I didn't tell you the starting point was 4? And let's see if I have that on the next one. No, let's just do it right now. And so what if instead of starting at 4, we just said that we were starting at the value a? How would that change things? And so we'll still do f of x equals the square root of x, but I want to find the slope at the point a comma square root of a, which we know is going to be on this graph because when you plug a in, you get square root of a out. Well, then we know that our a value is just equal to a. Our f of a is equal to the square root of a. And then our f of a plus h, which is the last thing we need, is going to be equal to the square root of a plus h. We can find our instantaneous rate of change now. Instantaneous rate of change. It is the limit as h goes to 0 of f of a plus h, which is the square root of a plus h, minus f of a, which is square root of a, all over h. Well, this we can now simplify, again, using the conjugate. Square root of a plus h plus square root of a. Square root of a plus h plus square root of a. Cleaning up the top, we still have our limit as h goes to 0. We are going to get a plus h minus a. On the bottom, again, we'll keep it gross. We'll have h, and then we'll have the square root of a plus h plus square root of a. This, again, we can simplify just like we did when we had the number 4 in there. The A's cancel, the H's cancel. And so we're left with the limit as H goes to 0 of 1 over square root of A plus H plus square root of A. And now we can plug in H going to 0, because now 0 going in for the H isn't going to give us a 0 in the denominator. When the H goes to 0, we're left with 1 over square root of A plus square root of A, which is 1 over 2 square root of A. That is powerful. And let's see what that power is. And so we got the instantaneous rate of change at the point A comma square root of A is 1 over 2 square root of A. When we think about what the graph of this looks like, we no longer need a starting point. Instead, we can say, let's let the point be A comma f of A. That'll be our starting point. And just like before, we can move this point to be wherever we want. Well, the equation of the line going through that point would be given by y minus f of A equals m times x minus A. And now we just need to know what that slope is. And our instantaneous rate of change, that 1 over 2 square root of A, is the formula for the slope at any point. So 1 over 2 square root of A. Now, no matter where we are on this curve, we are going to get the equation of the tangent line. We have found a way to find the slope of every single point on this curve. And the slope at any given point on this curve is given by 1 over 2 square root of A. That is what we call the derivative. And so this instantaneous rate of change is how we define the derivative of a function. And so here is 2 definitions for the difference quotient definition of a derivative. The derivative of a function f at a number a, denoted f prime of a, is given by the expression f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a over h, provided the limit exists. This is what we just calculated for the square root function. We just calculated the derivative of the function at the point a. However, often instead of figuring it out for a point, we'll calculate it for the entire function. And so the derivative of a function f, denoted f prime of x, is given by the following expression. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. We are going to use that formula a tremendous amount, because this is the formula which tells us the slope at every single point. And I don't want to give too much away, but when we think about how things grow and change, usually it's tied to the rate of change of the population. So we'll say the rate of change of the population is proportional to the number of elements of that population, or some other relationship. Because of that, we're going to get equations which are relating this derivative to functions themselves. And that's called a differential equation. We'll be seeing those starting in chapter 6. No, chapter 7. But for now, we just want to get familiar with this idea. And we'll start with just some notations, because there are a lot of different notations here. And so here are some of the different notations. It turns out calculus was independently figured out by a number of people. The main thing that made it so that calculus was able to be developed was the idea of the Cartesian coordinate system. The Cartesian coordinate system being this, the XY axis. Before we had the XY axis, which was developed by Descartes, we were basically using geometry in space, where we didn't have a way of analytically looking at how values compare to one another. We were talking about rays and circles and different shapes out in space. Descartes formalized this idea by saying a number line crossed with a number line gives us a place where we can map things very easily. And within 100 years of him coming up with that idea, everybody independently developed the idea of calculus, which is why we have so many different notations. Lagrange is one of the more popular ones. F prime of x, y prime. Those are very, very common. Leibniz also had some good notations, dy dx and ddx of f of x. We'll see this pop up every now and again. The idea being that this is a rate of change. This is a slope. And so this is really a ratio of rise over run. And we can treat it as a rise over run in certain circumstances. Euler had a notation which, it works. This is getting more into the idea of operation theory, using a capital D to represent it. The reason for this is because this idea of a derivative is really taking one function and it's giving you a new function out of that function. And so this is a way of notating that we're getting a new function from our starting function, kind of like functions of functions. And the last one is Newton. Newton was a fun one. He said, let's just put a dot over the top. And it works. It works great. And so if you ever see a y with a dot over it or an f with a dot over it, know that you're talking about the derivative of that function. We will actually see those starting in chapter 10 or chapter 7, and then again in chapter 10 if you take 356. But yeah. Here are some examples we can play with. We'll probably skip B since we already did a square root function, but let's definitely do A to start out with. And we'll just do a few of these to make sure that we feel comfortable with them. The square root one, or the absolute value one, is kind of silly, so we might skip that one. But let's do the x squared plus 2x. So f of x equals x squared plus 2x. Now remember your formula for the derivative. And so f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, when we want to calculate this, we need to figure out what f of x plus h is. We already have f of x, we already know what h is, but we don't know what f of x plus h is. And so let's write that out. F of x plus h, well, we would replace all of the x's with x plus h. So we would get x plus h squared plus 2x plus h. And we can clean that up. We'll get x squared plus 2xh plus h squared plus 2x plus 2h. And now we can plug this and this into our derivative. So we will get f prime of x is equal to the limit as h goes to 0 of f of x plus h, which is this, x squared plus 2xh plus h squared plus 2x plus 2h minus our f of x, which is x squared plus 2x all over h. Well, we can drop our parentheses. And we can drop these parentheses, but we have to remember to change the signs. There we go. And now notice we can cancel some stuff out. Our x squareds will cancel. Our 2x will cancel. And now notice we can factor an h out of the top. So we get limit as h goes to 0 of h times 2x plus h plus 2. over h. Well, now our h's can cancel. And then if we take the limit as h goes to 0, we'll be replacing this h with a 0. And so we end up getting 2x plus 2. Let's double check our answer using our good friend Desmos. And so we got that the derivative of x squared plus 2x is 2x plus 2. And so in this case, we can get rid of this function and we can replace it with x squared plus 2x. And to verify this, we can actually keep much of the same framework that we already have. We need an arbitrary point on this curve, which we have. So this is the point which is on this curve. We have this, which will give us the equation of a line. What we still need to deal with is we need to change our formula for our slope. And so our new slope formula is going to be given by 2a plus 2. And now, sure enough, no matter where we are on this curve, we're going to get the tangent line out of it. Excellent. I believe number 2 is tied to this. It says find the equation of the line tangent to f of x equals x squared plus 2x when x is equal to 3. And so let's do that real quick. And so tangent line at x equals 3. The best strategy for finding the tangent line is to use point slope form, because we should feel fairly comfortable with point slope form. So point slope form is y minus y1 is equal to m times x minus x1. In this case, we know our x value is 3. And so y equals, it's going to be an x minus 3. To figure out what y1 is, well, we have to plug that in here. And so when we plug 3 in, we get f of 3 is equal to 9 plus 2 times 3 is 6. This becomes y minus 15. And then the last thing we need is the slope. But remember, the derivative is going to tell us the slope. And so we need to figure out what f prime of 3 is. Well, f prime of 3 is going to be 2 times 3 plus 2. 6 plus 2 is 8. And that right there is the equation for the tangent line at x equals 3. If you want, you can put this into slope-intercept form. All you'd have to do is just solve for y. But if it doesn't say you have to, this is a great formula for it. This is point slope form. And this is the equation of a line tangent to this curve at the point 3, 15. Now, b we kind of already did, because having a square root of x minus 2 is not going to be much different than doing a square root of x. The absolute value one, that one's kind of silly. I wouldn't stress that one. But d is another good one. And so let's do d real quick. And so d is saying find the equation of the line tangent to f of x equals 1 over x. Or I guess find the derivative first. And then it says find the equation of the line tangent when x is equal to 4. And so f of x equals 1 over x. And so in order to do this, again, we need to know what f of x plus h is. Well, f of x plus h is going to be 1 over x plus h. Plugging that into our formula now, we get f prime of x is equal to f of x plus h, so limit as h goes to 0, of f of x plus h is 1 over x plus h minus 1 over x all over h. And hopefully you recognize this as a complex fraction because there are fractions inside of a fraction. In order to clean up a complex fraction, the best strategy is to multiply the top and bottom by the common denominator. In this case, x times x plus h. So we get limit as h goes to 0. For the first term, the x plus h's cancel, leaving an x. For the second term, the x's cancel, leaving an x plus h over h times x plus h. Well, now notice we can distribute this minus sign, which makes it a minus x minus h. Our x's will then cancel, and our h's will cancel, leaving the limit as h goes to 0 of -1 over x times x plus h. But now we can actually let h go to 0, and we get -1 over x squared. So the derivative of the function is -1 over x squared. Thinking about the visual for this, let's go back to our good friend Desmos. So now our new function is 1 over x, and we found the slope to be given by -1 over a squared. And sure enough, no matter where we are on this curve, it is going to give us the tangent line. And so this -1 over a squared is the slope at any value a. The second part to that, it said find the equation of the line tangent to f of x equals 1 over x when x equals 4. So let's see if we can find the tangent line when x equals 4. And we'll just do the same process we did for the last one. So we know that we're going to be using point slope form, which is y minus, and let's just write it like this, y minus f of a equals m times, or we could even replace that m with f prime of a times x minus a, because this is the slope and this is the point. We know that our a value is 4. We then know that this value, f of a, is going to be given by 1/4. And then f prime of a is going to be a -1 over x squared, so -1/16. And so the formula for the tangent line is y minus 1/4 equals -1/16. And then it is x minus 4. Excellent. And so that's the derivative. Doesn't that seem fun? It's a very, very, very big concept. And hopefully at this point you're recognizing that these might be difficult to calculate. I mean, we've just been dealing with some basic functions. What if we had a tangent in here? How would we calculate the derivative of the tangent? Well, good news, we're going to have a lesson next time, which gives us a ton of shortcuts for these. But before you start focusing on the shortcuts, I want to make sure you really, really understand what this thing is. This difference quotient definition of the derivative is a huge thing because this is combining limits to give us our slope. And this is how everything the rest of the semester is defined. It's defined based on this definition here. And so keep that in mind as you're doing stuff going forward. Here's some more questions to think about. What does the graph of a derivative look like? And so given a function f of x, the derivative is going to tell you what the slope of the function looks like at each point. And so for instance, if the derivative is positive at a point f prime of a, or if at a point, that means that f prime of a is greater than 0. That tells you that your starting function is increasing at that point. If the derivative is negative, that tells you the function is decreasing at that point. And if the derivative is 0, that tells you that it is flat at that point. Let's see if we can see what this looks like. So it says, for each of the following, find the derivative, then graph both the function and the derivative of the function. I'll save us some time by just giving you the derivative of these. And so for the first one, x cubed minus 4x, let's graph it here. X cubed minus 4x equals x cubed minus 4x. And so this is the function. The derivative of the function would be given by y equals 3x squared minus 4. And so let's make it so this one is orange and dotted. So the orange one is the derivative. And it turns out Desmos will actually graph derivatives for you. And so we could actually have just said y equals f prime of x. And notice it gives us that exact same curve, but it doesn't tell us what the equation is. What you want to recognize is that values in our orange one, values in our derivative function, are actually going to be corresponding to the rates of change of our green function. And so notice the values of the orange function are positive here. And so we have positive values on the orange function. That tells us that the green function is increasing at those points. When the function hits 0, when our derivative function hits 0 at negative 1.155, that is going to be corresponding to the value up here on our green function, where we are at our maximum, our relative maximum. And so that's where it becomes flat. Continuing, as we go down this curve, now notice it's negative. Our derivative is negative. And it's negative all of the way from here to here. Well, looking at our function, our green function, it is decreasing on that interval. And it decreases all of the way from negative 1.155 to 1.155. That's where the values of our orange one are negative. Then our green function is flat again. It's got a slope of x equals 0. And that corresponds to our slope being 0. Our orange function is 0 at that point. After that point, our green function is going to be increasing, which means that our derivative is going to have a slope which is positive. And so that's how these two things are connected. And this is going to be true no matter what function we have. Let's just make it so that this will be an arbitrary derivative, f prime of x. And let's put a different function in here. How about let's see, I want something a little bit more interesting. How about 1.2 to the x, and then I want to add a sine of 1/3 x. That might not be good enough. Let's just make it sine of x. All right, and so looking at this function, this is a very weird looking function, right? It is going to be increasing off to infinity over on this side. But when we look at this, we can kind of see the behavior of it. And so our green function is our main function. Wherever our green function is going to be having a high or a low point is going to be corresponding to when the orange function is at 0. And that'll continue all of the way throughout. And so anywhere where the green function is at a plateau, our derivative is going to have a value of 0. Notice between those values though. And so let's say from here down to here, the green function, our starting function, is decreasing on that interval. And looking at our orange function, our derivative, it has negative values on that interval. As we go on to the next interval from negative 1.7 to positive 1.8, our green function is increasing. And notice our derivative is going to have positive values for that. And so that's how these things are related. Notice eventually, after about here, the function just increases for forever. It no longer is going to be dropping down, or it's never going to have another plateau. It just increases and increases and increases. And that corresponds to the function being positive, or the derivative being positive after that. The derivative is never going to go back down to zero. It's just going to continue to increase. This works no matter what function we deal with. How about a quartic function? Let's do x to the fourth minus 4x cubed, or x squared. There we go. And so again, the green function is our main function, and the orange function is the derivative of that. And so for our main function, notice it starts by decreasing, then it increases, then it decreases, then it increases. Well, the values of our derivative function are negative, then positive, then negative, then positive. The slope of the green function corresponds to the values of our orange function. It's a hard thing for folks to wrap their heads around usually, and that's why I'm kind of taking it slow with this, but definitely play around with it a bit. And so here's some more challenging problems. Given a graph, can you describe what the derivative would look like? And this might be difficult to do on the whiteboard, so maybe we'll only do one or two of these. We'll just try and do it by hand real quick. And so let's start with that second one, because I think the second one's a little bit more interesting. And so I will do a quick graph of the function. Then it comes up. And let's make that one empty and open. And this is our f of x. And so this is our function. It's going to be going down in this direction, up in that direction. If we wanted to graph what the derivative of this function looks like, well, the derivative is going to be the slope. And so we could ask the question, what is the slope at all of the points on this graph? Over here, the slope is positive. And so we know we're going to be having positive values. Over here, the slope is 0 because it's flat. So that tells us we're going to have a value which is 0. Down here, the slope is negative. And so we know we're going to have values which are negative. But then it jumps. And starting here, it's going to have values which are positive. And so we know it's going to be positive. Moreover, if we look over here, the slope as we're going up to here is actually decreasing because it starts out fairly steep and then it goes to something less steep. And so our derivative function, f prime of x, is going to look something like this. Somehow it's got to start at positive values and end at 0 here. And then it has to continue into negative values. Because remember over here, our slope is negative. But then it's going to jump. And over on this side, our slope is positive and it's increasing. And so this might be an example of what that slope would look like for that function. Let's do another one real quick. And so let's say that we have a graph that looks like this. So this one, we will say that it is going to have an asymptote here. It'll come up, hit this value, then go down, and then it'll come down like this. And so if we wanted to figure out what the derivative function would be, what f prime of x is going to look like, we could do the same idea, just figure out what the slope is looking like at all of the different points. And sometimes it even helps to put a plus or minus sign just to make it so that it's clear. And so if we were to do a plus or minus sign on this, over on this region here, we can see that from here all the way up to here, it is increasing and it's getting exponentially large. It's going to be ridiculously positive as we approach this asymptote. Then over on this interval, all the way up to 0, it's going to be positive again, because notice it's still increasing. Over here, well, now it's going to be decreasing from here all the way to this asymptote, and it's going to get monumentally large again. And then over here, same thing, it'll be negative again. And so to graph our derivative function, we know that it's positive. We know that it's going to be increasing exponentially. And so it'll probably look fairly similar on this interval. But then it's still positive. And so it's going to be coming down like this. And then on the next interval, so it's going to be 0 here because our slope is 0 at that point. Here it's going to be negative. And so it's going to look something like this. But then it's still going to be negative after that. And so we'll have an asymptote, and then it'll come back down. This is roughly what that function will look like. Now we might be able to actually create this function. Let's see if we can create this function real quick. I don't know if I'll have any luck, but let's see if we can recreate this function in Desmos and see what it looks like. Eyeballing it, the function looks kind of like a 1 over x squared minus 4. Yeah, it looks pretty promising. Maybe we'll multiply it by something just to make it so it's a little bit more visible. There we go. So we can see that we have the function increasing here, and then it's going to have an asymptote, and then it's going to be decreasing there. If we want, we could even make it a little wider so that we can see it even better. And so the derivative of this function looks like this. And so notice it's positive, and it's positive, hits the 0 mark, which is where the green function is flat, and then it goes negative and negative. And so that's the idea of graphing the derivative. The idea is figure out what the slope looks like, figure out if it's increasing or decreasing, maybe try and figure out how fast it's increasing or decreasing. And once you've got that, you'll be good to just plot the points. Another concept we have is the idea of differentiability. It's kind of like continuity, all except not everything that's continuous is going to be differentiable. And so a function is said to be differentiable if f prime exists. It's differentiable on an open interval if it's differentiable at every point on that interval. If a function is differentiable, then it is necessarily continuous, but the opposite is not true. Just because something's continuous does not mean that it is differentiable. And here are 3 different cases to look out for. And so cusps are not differentiable. A cusp is where you come up and meet at a point and then you go back down, or there's some drastic change in the rate of change. It's still continuous, but it is not differentiable. And here are 2 examples. The absolute value of x, that's a function that comes down to a point. At that point where it makes the V shape, it is not differentiable. It's differentiable everywhere else, just not at that one point. Another example is e to the negative absolute value of x. Absolute values tend to have those things. Another example is discontinuities. And so if you have an asymptote, it's not differentiable at that asymptote. If you have a function where it is doing a step discontinuity, where it's jumping, then it's not going to be differentiable at that point. Basically, if it's not continuous at a point, it is not differentiable at that point. Another one is vertical tangent lines. And these are a little bit weirder. And so let's take a look at the cube root of x to see what this looks like. And so if we look at, let's hide this one, the cube root of x, that would be x to the 1/3 power. This is differentiable everywhere except at this one point, at 0, 0. And the reason is we're going to be getting a vertical line. I was getting vertical and horizontal mixed up. You'll get a vertical line when you try and calculate the slope, but that would mean we'd be dividing by 0. If we graph this out, we can see that we're going to get a slope which is going off to infinity. And we can't say that we have a slope which is equal to infinity because infinity is not actually a number. It's a value which you can approach, but goes on forever and ever and ever. And so really it's a limit, not a number. And so at this point, we would say that it's not differentiable at 0, 0 because the derivative does not exist. And if you want, these are the same graphs that we did last time when we were talking about continuity. Basically everywhere where it's not continuous, it's not going to be differentiable. The only one where it's going to be continuous but not differentiable is going to be at 0 here. And so notice at this one point, we can see that it's got a cusp. The limit from the left and the limit from the right don't match up, which means that the derivative does not exist at 0. The last thing I'd like to talk about today is the idea of higher level derivatives, because we have a lot of different ways of representing these things. And so we'll start with the function level. And so a function, we can typically write it as f of x or y, and it represents a value or a position. Oftentimes, I like to think of it as a population, because most of the time, that's what we're actually talking about. We're talking about a population of cells, or we're talking about populations in a more general sense as far as an amount of carbon. The first derivative represents the rate of change or the velocity. And these are given in terms of spatial by being f of x, but in order to make it related to time, you just make it f prime of t. But these are the different notations for our first derivative. We have f prime of x, y prime, d dx of f of x, dy dx, big D of f, or y dot. And again, they represent rate of change, oftentimes with respect to time. And that's what the velocity is. Velocity would be the rate of change of position with respect to time. The second derivative represents the concavity or the acceleration. And so how fast is the rate of change changing? And it would be given by f double prime of x, y double prime, or d2 dx squared f of x, or d2y dx squared, or d2f, or good old Newton, y double dot. All of those represent the second derivative. We will be dealing with the second derivative a little bit in this course. In Math 356, you'll be dealing with it more, but you will see it pop up from now and then in this course. The third derivative, f triple prime of x, y triple prime of x, and all of these other ones, and good old Newton with the y triple dot. Represents the rate of change in concavity or the change in acceleration. This is often referred to in physics as the jerk force. When you think about it, humans can't feel velocity. We're standing on a planet that is going thousands of miles a second, and so we don't feel that. What we feel is we feel when there's a change. And so if you are in a vehicle, you will feel the change in acceleration. If you hit the brakes, you'll feel that. And that's what the jerk force is all about. It's the idea that you can feel these changes in acceleration. It represents the rate of change of acceleration or concavity on velocity. The third derivative, we will not deal with a tremendous amount. Most of the things that we'll be modeling in this course can really be modeled using a first derivative and multiple populations. And that multiple populations is really the key. Second derivatives do come in handy when you're talking about physicsy stuff. They pop up a lot. Third derivatives, they also pop up, but second derivatives, that's really where it's all at. And higher derivatives, I mean, again, you can do higher derivatives as far out as you want. If you see a function with a number in parentheses as the exponent, that means it's that many derivatives. And so if this were f with a 20 in the parentheses, that would mean the 20th derivative. Same with all of these other ones. And so this n would just correspond to whatever value it represents. As far as what a higher level derivative represents, I mean, did you ever see Inception? This is the rate of change of 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 the rate of change. Or you could talk about the concavity of the velocity of the concavity of the acceleration. There's a lot of different interpretations for them, but you're not going to be using them that often. I mean, once you get past second derivative, the value in understanding them starts to become little, because then we're just talking about how the rate of change of the force is looking. And forces do change with respect to time and with respect to space, but usually you're not going to be dealing with the same variables. Usually you'll be talking about higher order derivatives in multiple variables. And so you might be taking 2 derivatives with respect to space and then 1 with respect to time, or maybe 3 derivatives with respect to time and then 1 derivative with respect to each of the spatial components. And so that's something we won't have to worry about in this course. You might see 1 or 2 problems related to higher order differential equations, but yeah, you're not going to have to stress it too much. And this last question here is talking about this idea, differential equations. Differential equations are used to model a number of physical and biological phenomena. And we are going to be dealing with differential equations later on in this course. This is a very, very simple example. Let f of x equal x cubed minus 6x. Show that y plus y double prime is equal to x cubed. And so f of x is equal to x cubed minus 6x. Show that y plus y triple prime is equal to x cubed. And I'll do this one using a shortcut just to make life a little bit easier. And so we know what our function is. And so this function f of x is corresponding to y. What we still need to figure out is what y triple prime is. And that means we would have to take the derivative of this function to figure out what f prime of x is. And then we need to figure out what y double prime of x is. And then we need to figure out what y triple prime of x is. And it's a good exercise to actually go through and take the derivative of this 3 times. But since we don't have the shortcuts yet, I'll just give you the cheat for it. And so the first derivative is going to be 3x squared minus 6. The second derivative is going to be 6x. And the third derivative is just going to be 6. Did I write this problem down wrong? I did. It wasn't a triple derivative, it's just a second derivative. There we go. That'll make things a little bit easier. I was going to say, this isn't going to cancel out. Oop. But now it should when it's a second derivative. And so in this case, we didn't need to take the derivative 3 times. We only need to take the derivative twice. And I would recommend you actually go and use your difference quotient definition of derivative to see if you can take the derivative of this thing. It will get a little bit tedious, and you'll have to recognize that x plus h cubed minus 6x plus h is equal to x cubed plus 3x squared h plus 3xh squared plus h cubed minus 6x minus 6h. And so this will be a little tip to figure out how to do the difference quotient definition for this one. But once we have this, in order to show this property, all we have to do is plug the values in. And so y plus y double prime is going to be equal to x cubed minus 6x. And then it's going to be plus our second derivative, which is 6x. And notice stuff cancels. And there we've proven it. And so that's an example of a differential equation where you're just trying to show that it's true. Eventually, we'll actually have to figure out these solutions to these things just from the equations themselves. And that is much, much more difficult. But that brings us to the end of today's lesson. And so today we covered the fundamentals of derivatives. Back when I'd be in person, we would actually be doing the, what's it called? The first exam after this. But because we're doing it in the online environment, you don't have to worry about that. And so for now, just make sure that you feel very, very comfortable with the idea of derivatives. In the next video, I will be showing you the shortcuts so that you'll be able to take the derivative just as quick as I was able to do this one here. But that'll be next time. Make sure you get your homework going and you should be all set. Take care of yourselves.